Thank you very much for the introduction. It's a great pleasure to actually be here. I'm sorry I have to do this in English. Perfect, thank you. I hope you'll be able to understand. One of the fortunate things about robotics is that it has lots of videos. And so you'll be able to see with pictures some of the things that I'm actually trying to say to you. So just let's see if this works okay. Just a second. So, go close. Great, thank you. It's okay. So I'm from the Italian Institute of Technology, but maybe as you can hear from my accent, I'm not actually Italian. I'd like to thank all the organizers of the CHIOS Festival. I'd also like to thank the Italian Embassy in Greece for their invitation to actually come here. The Italian Institute of Technology is based in Genoa, which historically has, I believe, lots of connections with the island of CHIOS. So what I want to do is to look at robotics, its impact on humans, and a little bit on humanoids. And so we'll cover a little of the area of robotics in general, and just try and give you an overview of what robots can do and what they'll be able to do in the future. So to look a little bit in historic context, the idea of a robot actually goes back a long way. It goes back actually to this part of the world. In myth, Hephaestus actually created the first robot, Talus, 2,500 years ago. In mythology, in Greek mythology, you created an artificial man made from bronze to be able to guard the island of Crete. But it wasn't just in myth that this actually happened. In the Greek world, there was a lot of actual engineers and scientists who were actually creating robots 2,000 years ago. So Hieron of Alexandria, who lived about 2,000 years ago, sometime between the 0 and 100 AD is what they estimate, created many, many very advanced systems. One of them is the Heliophile, which actually is the first steam engine. So steam engines were actually created in Alexandria by a Greek scientist almost 2,000 years, 1,800 years before it was actually created in Europe, in the rest of Europe. So there was actually predating. And much of the technology, which actually forms part of our robotic systems, was actually available. We had hydraulic systems, we had pneumatic systems, we had mechanical systems. People often, when they talk about robotics, look at Da Vinci, and Da Vinci was absolutely a genius in terms of developing robotic systems. But this is actually 1,500 years before Da Vinci. And this technology already existed and essentially got lost for that amount of time. And it wasn't just Hero, it was Philo, it was Sebestius. In truth, the first real robot wasn't actually with what we actually see as robots now. First real robot wasn't created until the 1950s. So it's about 70, 75 years. It's actually a relatively recent technology. And so what we'll actually do is have a little bit of a look for, could you try the next one? So just before I go on to show you a little bit more, I wanted to also put this again in a context of Greece. And so just recently, within the last 6 months, there's a Hellenic robotics center of excellence called Heron, which is actually formed with the Athena Research Center, partly funded with the Italian Institute of Technology and also with KIT, the Caldwell Institute of Technology. So this is actually funded. It's got a little bit over 35 million from the European Union, from its Teaming for Excellence, also from the Greek government, from the General Secretariat for Research and Innovation, and also from private sponsors. So there's been a large investment in that. The concept behind the Heron Research Center is to advance science and technology of robotics in the age of AI, age of artificial intelligence. Mainly focuses on four main areas: safety and rescue robotics, field robotics. Field robotics just means any robot which is not inside. Essentially, it's outside. That's in agriculture, in shipping, and transport. Healthcare robotics, and then social robots. Social robots are robots which are designed to interact with people, to understand that interaction, to understand the well-being of people, create sort of some social context. Heron aims to positively impact the technology, economy, security, education, and health of Greece. That's what it's designed to do, and it works with us in IIT and with people in KIT to try and bring that technology. There are many great roboticists working here in Greece, but it's to actually bring that and create a whole dynamic system on that. Next one, please. So just looking at what makes a robot, what makes a complex, high-performance robot. This is not the types of robots that we're actually talking about in industrial applications, though much of the technology is actually the same. But these are high-performance robots. So you can see them. They're things like humanoids, but they're not just humanoids. And so we can actually start. We look at the materials. And so if the laser works, oops, now it works. Backwards. Yeah. So just wanted to pointer. Yeah. Okay. So looking at the materials. The materials, essentially, it's what when we look at robots, we call it the skin, it's the bone, it's the ligaments, it's the tissue. It's what the robot is actually made of. Mostly it's metals, sometimes it's plastic. Sometimes we use additive manufacture. So we use modern manufacturing methods to be able to do this, which actually allow us to create robots in much more organic ways. They are much lighter, makes them much more high performance. But we use a number of different materials. Typically the most common is to use aluminium steel, but we use magnesium, we use various different types of plastics, lots of different materials. We mold those together to actually create the robots. We have computer hardware. So if we actually look at each of the little boxes, you see some of the circles are outlined in green, some are actually in red. The green circles essentially are the hardware of the robot. Physical, you can touch these particular components. The red portions, that's the software. And so we'll come down to that and I'll actually show how the hardware and the software, they blend themselves together to create a robot. A robot is a constitution of both the hardware and the software. It's the brain and it's the actual physicality of the robot. So the computer hardware, that is like a computer that you would actually have, your normal PC type. So it's a computer, it's the brain tissue. We have the anatomy. Robots originally started off, they looked like just an individual arm. But now we create robots which look like humans, we create robots which look like animals, we create robots that look like nothing, we create robots that look like snakes. They can look in any type of organic style, so we use organic inspiration quite often to design the robots. And that's their anatomy, that's the physical structure of the robots. The kinematics. The kinematics is how you move the joints, okay? And the kinematics and the anatomy go very close together. So when I bend my arm like this. But there's no reason why a robot should be restricted like this. A robot can actually bend its arm completely the other direction, okay? All the way through. There's no reason for those restrictions. Robots can have different kinematics. So it can have the same skeleton, but different range of motion. A robot wrist can continually rotate. So we do this through the robot joints. We have modeling and simulation. This is essentially where the robot plans in its mind what it's going to do. This is a form of software. Okay, so if it wants to do a task, it thinks about it beforehand, but it's not artificial intelligence. It's just about planning the actual task. Then on the other side, we have the actuation. The actuation are the muscles. When I said about in ancient times we used pneumatics and hydraulics, now we tend to use electric motors. Okay, sometimes we use hydraulics. Some robots still use hydraulics. A few use pneumatics, but mostly they use electric motors. And high-performance electric motors are very essential. Sensing and sensors. Those are the eyes, the ears, touch, taste, and smell. Okay, And everybody thinks that the eyes and ears are the really difficult things to actually do, but in truth, they're relatively easy. The hardest thing to actually do is touch. Touch is by far the hardest sense. It's one which in robotics, we have great eyes for robots. We have wonderful ears for robots. Robots can even smell. They have the capacity to be able to smell and be able to detect. What they struggle with is touch. Okay? You cannot create, there is no robot which creates the human hand with its tactile sensing, and absolutely no robot which actually is able to create a skin which covers the whole of a body. Okay? You can't do it. It's too difficult at this moment in time. So it's actually, if you think what the really hard thing to do, it's manipulation and touch. Then we have artificial intelligence. Now, people often talk about robotics and AI. And what you can see here is that AI is actually just one of the little circles inside robotics. And robotics is one of the little circles inside AI. They are interconnected, but they are completely different. One is not a function of the other, they don't link together. We have high-level control. High-level control is things like spine control, reflexes. It's actually non-conscious actions. So when I'm walking around here, I'm not thinking about how I walk. Okay, those are motor responses, but those are controls. Those are software. And then we have actually joint level control down at the nerves, how we actually send the signals directly to the nerves. Inside this, we have a disk which rates, so we have the technologies which we just looked at. We have the intelligence which goes with the various software. We have the tasks, the jobs that the robot wants to do. Traditionally, robots did manufacturing. That's what they did in the very early days. They were designed to go into factories to do manufacturing tasks. Now, that's a very, very small portion of what robotics does, and we'll have a look in a few seconds at what we actually do. And then we have the environments they actually go into. So we saw some previous presentations talking about nuclear environments. Robots go into nuclear environments. Too dangerous for people. If we don't send robots in, nothing happens. Robots go into biologically contaminated. They go into chemical environments. They also go into agricultural environments. They work in fields. There are now robots which actually go out, do fields, and can actually do things. They can work. They go to the moon. They go to the planets, so they can actually do interplanetary. Without robots, we wouldn't be able to do much of the interplanetary science that we're actually doing. Thanks, Ron. So this is just showing you a little video of how some of our robots evolved over a 10, 15-year period. So we started at the top left, and we have a very small robot. This was a baby robot designed to be about the size of a 4-year-old child, and actually inspired by a child. The idea was we would build a physical robot and be able to put the intelligence into that to be able to model the child. Building the robot was difficult, but we could do that. Building the intelligence of a 4-year-old child, almost impossible. We're nowhere near it. Even with all the best AI we have, there is nothing we can actually do at this moment in time to be able to create the intelligence of a 4-year-old child, or even an 18-month-old child, or any child. The second one, Coman, physically what we were doing with the second one was we were making it compliant. You see that the person actually interacts with it. It's able to be soft. Robots, traditionally, you don't go near them. They're too dangerous. Robots will kill you, right? If they actually hit you, they fly around really high speed. They're really dangerous. This robot, really safe. Children play with it. It's a really soft environment. The Walkman, so these are robots were small. The Walkman we actually see there, 2015, this is a big robot. This is nearly 2 meters tall, 120 kilos, okay? Very, very strong. Don't go near it. It is a big, scary robot. People love to have their picture taken with it when it's turned off. Nobody wants their picture taken on when it's turned on. Nobody goes near it when it's turned on. It's like an American footballer, but bigger. And you just don't go near it. Then you have the Coman Plus. And the Coman Plus is actually a smaller robot. It's about 1 meter 50, 1 meter 60 tall. Weighs about 60 kilos. It's actually as strong as the Walkman. Walkman's 120 kilos and 2 meters tall. 4 years later, we can build a robot which is half that size and still as strong. And I'll show you how strong it is in a few minutes. Then we can see robot. This is a robot actually driving a car. Okay, so you don't have to have autonomous cars. You can actually have robots driving a car. It's a totally pointless exercise. You'd never do it. But it's just to show that it can be done. It was part of a competition. The Centauro one, can you just go back and start it back in one of the videos? Can you just take it back? Yeah, just go backwards. Go back. Yeah, and then forward. Right, the Centauro. So the Centauro is inspired by Greek mythology. Okay, the robot is actually a part of a project. It's called Pholus. And so it was actually funded by the Italian Navy. This is actually at Jeff Bezos' special summer retreat. He got invited to that. This robot is able to walk. It's a centaur. It's got 4 legs, can walk like a dog, but it also has 2 arms. On the robots on the bottom, we see quadrupeds, 4 legs. They are dogs. They are sheep. Here you can see one which is actually quite strong. This is towing an aircraft which weighs nearly 5 tons. So you can see the robots can be very, very strong. The one in the middle, I don't know if you saw it, it's just showing it can roll over and how fast they can actually go. And these are some more recent robots where what we've been doing is taking the concepts and developing the MARM robot. MARM robot, just the middle one there. This is actually designed for maintenance of satellites. So in space, when you have to go into satellites, have a satellite, and you have to go out and you have to do maintenance on the actual solar panels. This is a robot to do space maintenance. So as I said, robots are actually a big intrinsic part of space technology. Great, next thanks. And this is just showing you a little. So let me see if the pointer will work. Right, do you have a better pointer? A better pointer with a laser? The battery's done. Oh, back. Yeah. Okay, this particular. You just need to go back to run the video. And forward. Right. This robot arm is about the same weight as your arms. Okay? Weighs about the same as you do. It's the arms that actually go into this robot here. Right? And on the end of this robot, this is 10 kilos. There's a 10 kilo load out here, and it's just moving 10 kilos in one, 10 kilos in the arm. This robot is incredibly strong. It's one of the strongest robots in the world for its weight. The robot beside what you can actually see, it's being what we call teleoperated. Person moves, the robot copies every motion of it. A walking robot, this is running, you saw before. This is showing, this particular robot was actually doing karate. And so the idea was that if it had to go into a building and the building was blocked, it can go in. This one is actually doing planning. It's actually thinking about the process. It doesn't know how to get through the environment. This one's just climbing on steps. And so it's actually, you see the way it's changing its wheels? And it's changing its wheel structure. It's an intelligence, but it's not artificially intelligent. Because the robot is actually learning from models. It doesn't learn in the way that we talk about artificial intelligence. In the same way that if you open a door, that's an intelligence process, but we would never consider opening a door as part of our artificial intelligence. Next please. So I also want to look at how robots can impact on healthcare. And there's many areas in which we can actually impact on healthcare. We can actually have impact on surgical systems. So we can actually look at robots for surgical interventions. I'll show you a few little operations of that. Robots for telehealth. The idea with telehealth is that your doctor is in one place, you may be 1,000 kilometers away, and the doctor can actually do the diagnosis, the doctor can do the treatment, the doctor can even do the surgery. You have social robots. So this is particularly with elderly or people living on their own. The idea being that the robot is actually in that environment and can actually take care of the people, just report back on what they can actually do. Robots, service robots, this is robots just to be able to go into hospitals. This was particularly during COVID. The idea was that the robots would actually go in to the hospitals. They would be able to move around the hospital. They don't spread infection because the robots, you can spray them down. And yet you can do many of the different things, delivery, taking of logistics, taking drugs backwards and forwards. And then we have robot-assisted technologies. This is exoskeletons. I'll show you a couple of slides on that in a second. Okay, next please. So this is a surgical system. Up on the top left, up on the top left, this is the traditional setup. This is an actual operation in place. This is an operation on the larynx, on your throat. Okay, it's a cancer surgery. to remove cancer on the throat surgery. And this is the way it's traditionally done, top left. And what we wanted to do was to augment the surgeon's capability, to help them with intraoperative planning, to augment the planning and execution, and increase the precision. And so we developed a number of different robotic technologies, and there's many different types integrated into this. Head-mounted displays, tablets, VR, robots, higher precision. Here you can actually see, this is actually a demonstration. This was with a cadaver. And what you can actually see is 3D operations. What we can actually do with this is an example, we can actually automate the laser. So instead of the surgeon actually doing it, the surgeon plans the path, and then he goes back over. And what you will actually see is, in the first one, the yellow marker shows the trace, and then the laser, once the surgeon's happy, he turns it on. He can move backwards and forwards. And so instead of having to continually move his scalpel, the actual robot moves backwards and forwards. In the second one, we can see here, what we do is we create safety regions, an area that you don't want to cut. Okay, dangerous area, nerves are there or something. And so you can actually screen this off, and the moment the laser goes into that point, it turns off. So you can never actually accidentally make an incision. And then the third area is what we call ablation. Ablation is really removing a surface texture. You just go back and back and back and rub it away. And this just essentially removes the actual surface, and you can actually plan how deep you actually go. So if you were doing ear surgery and you needed to go down 0.5 millimeter, you can just go back and back and back until you've removed 0.5 millimeter. So the precision is way beyond what you can get with a normal surgeon. Next, please. So in the previous presentations, we talked about 5G, and we do 5G surgery. This was actually the first 5G, we actually did the first 5G surgical test in the world back in 2019, reported in 2020. And this is in Milan. Milan at the time was the most 5G connected city in the world. And so you had surgeons at Vodafone Village, and you had the patient who was actually at San Raffaele Hospital, 15 kilometers. This is all done over 5G. This is not done with any cables. This is a 5G system. This is why. And so what you actually have is a variety of different types of robotic devices, a tablet, Omega, that's a haptic device, it's a touch device, a head-mounted display, and then you have a laser. And you actually do this over the 5G. And so we did this in front of a live audience at the Vodafone Village. And if you go to the next slide, please. This just shows it. So this top one is in front of the live audience. This is actually the surgery actually taking place. And so we had 2 surgeons, and they did what's called a cordectomy, which is removal of the vocal cords because of a tumor. And so they did 2 types of cordectomy, and they did this, and they were able to do this. I didn't show the one, I don't show the one with the cadaver on the slide, so just in case, this is just showing a section of the throat. But they did this. And the actual time to do the operation, what they said, was exactly the same as they had if they were doing normal operation. They had 10 minutes of training on the system before they actually did it, and that was all they needed to actually adapt to the robot. That was how easy it was. Next, please. Okay, so this is what's called peripheral intravenous catheterization. When you go into hospital, they try to put a line into your arm. There are 5 billion of those done every year. First attempt fails 50% of the time. After 3 attempts, they're supposed to get another nurse or doctor in to actually do it. And after 3 attempts, really, it's. We were asked to do this for children, for newborn babies. This is where the original project came. They had newborn babies, actually preterm, 25 to 30 weeks, and they couldn't get the catheter in because their veins are so small. And so we developed a particular technology, and what the technology does is it detects, when it's actually inserted in, it's able to detect blood, the presence of blood in the vein. Okay? And so, if you just go back and forward again, the video should run. Right, forward. Okay, so this top is just showing, this is normal catheterization. The bottom one, this is the researcher who was working on it. Just press again. Forward one. Okay, so this is the researcher who was working on it. As he puts in, you will see a green light up. just over in the right-hand side. It'll go green. Right, that is in the vein. So it's detected the presence of blood, and it knows, so the nurse, the doctor actually knows they are in the vein, they don't go any further, right? So the first time they did this, usually when you try it the first time, success rate is 12%. When we had engineering students do this, so medical students, the first time they do it, 12%. Engineering students, the first time they did it with this system, 86%. So there's no comparison. The next one actually automates this. So once the needle, can you just press it again? Yeah, please. Next one, this is just on a baby model, but this is to show that what it was designed for. It's actually, the system inserts the needle, detects the presence of the blood, and automatically detaches. So you can actually see there's simulated blood, so you can see it pulsing. The third system, which again, the second one was licensed to a company, the third system actually uses cameras to detect the presence of blood and is able to move left and right to be able to detect that. So we can skip through that one, go to the next one. Yeah, it's okay. Next, thanks. Okay, so if you're doing abdominal surgery, okay, when you go into the abdomen, surgeons sometimes get lost. Up becomes down, left becomes right. They don't always know where all the bits and pieces are. It's not good news to tell you, but it's actually true. So what we develop is a GPS system, so you don't get lost. When you're driving from A to B, you use GPS not to get lost. We have a GPS system which actually works inside the abdomen. So here we're just showing it on a phantom model. We do actually have a version where we do it on a pig. So we do have animal trials that we do it, but I'm not going to show you those. But what we can actually do is inside, so before you actually have the surgery, you have a CT or you have an MRI, which actually works out exactly where all the vital organs and all the various different nerves are inside your body. When you go inside the abdomen, you actually then map one onto the top of the other, and the surgeon is able to know exactly where they are. The thing is, if you've got an expert surgeon, he doesn't need it. So the person who knows how to drive really well doesn't need GPS. But when you're a new driver, the young surgeon, what you use is the GPS, because it tells you, don't cut there, don't go there. Right? So we have this GPS. This is now being created as a new startup company. Yeah, next one, please. This is, okay, so there is a condition called twin transfusion syndrome. When you have twin babies, here, sometimes what can happen is their blood supply gets intermingled. And when this actually happens, one of the babies grows and one of the babies doesn't. And this is because this baby is taking all the blood and nutrition from the second babies. The second baby usually dies. And what we can actually do with this particular system is we're able to go in, we're able to map the critical veins, and then using the lasers, same lasers we use on the throat, using the lasers, we are able to cauterize that vein and stops the blood flow from the first baby to the second baby, and the first baby now can start to grow again. So it's actually a way of saving the life of the baby that wouldn't develop. Next, please. As I said, we work a lot with pediatric. We were asked by the local hospital in Genoa to actually look at brain surgery. So this is for encephalitis. And what they would do when they do brain surgery, because the baby's skull is, a newborn baby's skull is so small, the surgeons can't do it. Everything's too small, everything's too delicate. And so what we actually developed, and so this is just a prototype, but this is a prototype of a system which is actually able to line up. So you can do an MRI, CT, work out exactly what you want to do beforehand, and then the robot is able to guide that. The robot doesn't do the surgery. The surgeon still does the surgery. The robot guides the surgeon. So in all of this, the robot never does the surgery. It's always the surgeon. They're fully in charge, so don't worry about this. Next, please. This particular one, so this again is for throat surgery. And what we're able to do here is we're able to use imaging techniques to be able to predict the limits of a cancer. So you can see the white area is quite clearly a tumor. You've got the healthy tissue on the right-hand side, but the difficulty is knowing the boundaries. knowing exactly where the boundaries are. And so we are able to use imaging techniques to actually improve the boundary. What we can also do, the system I showed you previously that could detect blood, it's actually able to detect the difference between healthy tissue and malignant tissue. They actually give different characteristics, and so we're able to actually test that. And at the minute we're doing clinical trials on testing that to be able to test the boundary limits on malignant tissue. The idea behind this would be that if you had to remove, you would remove only malignant tissue. You would never damage healthy tissue, so the patient has a better outcome. Next, please. This again is a tracking system. I showed you the ones before when we had the GPS. What we can also do is we can also mark vital parts of the anatomy, and so we can highlight that for the surgeon so that when they actually look at this, they won't make mistakes. Okay, what all of this is about taking surgeons, particularly new surgeons, and making them as qualified as the best surgeons you can have. So essentially you will always have the best. And so the robots are able to help us do this. Next. Another one is musculoskeletal disorders. Okay. So this is about back injuries. Back injuries are the biggest cause of problems in any industry. In Europe, 2% of GDP is lost from back injuries. And so what we are able to do next, we are able to create a series of exoskeletons which actually offload the actual weight that the person is actually doing. And so we've done this in tests. Yeah, go next. This is for elderly people. So one of the problems that elderly people get sometimes is after post-stroke, they have difficulty lifting the leg high enough to be able to walk. This is a textile-based system that allows you just to lift your foot just 1 or 2 centimeters to be able to help with that. Next. This is a system being tested on a railway. Okay, just showing that it works with workers. These are industrial systems, and I'll just go to the last one. Next one. Okay, so this is one which is very important for the city of Genoa. 8 years ago, the main bridge in Genoa collapsed. This is the bridge when it's collapsed. There were 43 people killed in the collapse. When the bridge was rebuilt, they actually put robots onto this. So can you just press one more time? And so these are our robots actually on the bridge. They do maintenance, they do inspection, they do maintenance, and they do cleaning operations. That's it. Thank you. I'm sorry I overran.
Thank you very much for helping us dive into the world